Hello everyone, and we are back and we are going to be going through our pre-lab for thermal energy storage. Whoops. Let's do, there we go. For our thermal energy storage lab. So again, this will give you all the pre-information, go through a little bit. There's going to be another video of actually me performing the lab, and there's going to be another post-analysis video as well. So stay tuned and be sure to watch essentially those sequence of videos. So thermal energy storage. We are going to be investigating a particular type of thermal energy storage system, and those being phase change materials. So PCM materials are very unique in that basically what we do is we harness, basically we store energy and then we retrieve it later when it's required. So PCMs go through essentially a phase change. So a PCM will basically melt at a particular temperature. So as, for example here, the temperature rises. So we have a PCM in a solid state. Temperature rises beyond the melting temperature, it melts. Melting is an endothermic reaction. So endothermic, we absorb energy from the environment. As we absorb the energy from the environment, the temperature will eventually begin to fall because we're absorbing energy. And that material will also, as the temperature falls, if it falls below the melting point, then we will solidify. Solidification is exothermic, so temperature is released into the environment. So basically, this absorption of energy from the environment will seek to drop the temperature. When it solidifies and it's exothermic and releases energy, it will raise the temperature from the environment. So we're basically, a PCM is trying to keep the environment at a stable, specific temperature, and that is the melting temperature of the material. So this has already been used and embedded in a lot of wall material, and we're going to see many applications where it's already in use. But this is a very, very powerful and relatively simple technique that can be used for a myriad of applications. So again, it's kind of this store it and retrieve it when it's necessary. So similar kind of concepts would be used. It's to reduce essentially dependence on the grid. So it reduces your electricity use and all of these other kind of good things. Now, there are three types of thermal energy storage systems commonly: sensible, thermochemical, and latent. We're going to go over all of these, and we are going to focus on latent heat storage in this lab. Sensible heat storage, effectively, we store and retrieve energy from our specific heat capacity. So water is the material with the highest specific heat capacity. So it takes a lot of energy to change water 1 degree Kelvin or Celsius equivalently. So this is why if you live near the coast, like us in beautiful Humboldt, the temperature, the weather is very mild, and it's moderated essentially by being close to the ocean. So you don't get these big swings like if you live near the desert, right? Deserts can have intense periods of heat during the day, and the temperature drops significantly during the night because that specific heat capacity is much lower. Same reason why the crust of a pizza is basically not as hot as if you bite into the cheese, which is wet and has the water. And again, your temperature is essentially, that's a different concept. You can also have thermochemical storage. So thermochemical storage, and again, you're kind of limited in terms of, we'll see what the limitations of this are in a second. But thermochemical storage, it's like kind of like rock salt. So if you've ever thrown rock salt, if you've lived in a place where it's icy, and it basically uses chemical reactions to basically release and store as it goes through that chemical reaction, temperature is generated, and then you can essentially harness that energy. So the problem with thermochemical storage is you have to keep supplying essentially those reactants and to basically retrieve, again, the endothermic or exothermic reactions. But what we're going to look at in this lab is latent heat storage or phase change materials. So we are going to harness the hidden energy, the latent heat of fusion. So basically, we're going to harness the energy from when we go from a solid to a liquid. So when we undergo a phase change, that material undergoes an enthalpy of fusion, and there's a large amount of energy released that's hidden in the material. So you can see some examples here. We are going to be looking at fatty acids. So a good thermal energy storage system will have an enthalpy of fusion, delta H, of around 150 kilojoules per kilogram. We want a higher enthalpy of fusion because if we want to keep our temperature at the melting temperature, if we release and absorb a lot of energy into and from the environment, we could bring down the temperature quicker or raise the temperature quicker back to our melting temperature. So that's kind of the key metric. You can measure the enthalpy of fusion with basically a differential scanning calorimeter. But for this experiment, we already know, and we can look up the enthalpy of fusion for the various concentrations of our materials. But we already know ours is a good PCM material. The one thing we're going to have to look at is our phase diagram to pick our specific composition, and then also to look at some of the thermal stability curves that we can observe here. All right. So these are some of the ideal characteristics for a good PCM. So the biggest is we have to have a melting point in that desired operating temperature for our application. We need high latent heat diffusion, which we have for our materials. High specific heat would be good, high density. Supercooling, we want it low. And we need thermal stability. So it needs to be, when we heat it up and cool it down, it needs to kind of show no hysteresis. And we'll see that in a little bit. We can look at our PCMs here. So this is kind of the difference. Look at this. This is water. This is the best sensible heat storage system. And so our limit here at a specific temperature would be, this amount of energy stored. But if we just use a PCM, and if we harness, again, a PCM with a melting temperature at this particular application, right, we're an order of magnitude larger than the best sensible heat storage system. So that's kind of the key concept that we want to reinforce here. So yeah, PCMs have used a lot of bedding. So the new beds, especially Tempur-Pedic, others, they've embedded PCMs to keep essentially your mattress cooler. It's been used in construction materials. It's very famously been used to prevent milk from spoiling in India. And this was actually a MADMEC competition, basically MIT has a materials competition, and undergraduate students participate in it, and this was basically an offshoot from that. So really, really cool myriad of applications. You'll choose the one that you want. So we are going to develop a phase diagram similar to this for our, effectively, our system. So we are going to be working in this lab with lauric and stearic acid. So these are two fatty acids. Stearic acid has a higher melting point because we have more carbons and thus more van der Waals bonds than stearic acid does. But we're going to be combining these based on mass. And these are just fatty acids. These are, you can think of them as very, very, very small polymers. And we can look at this here. Now, we're going to be melting these materials. We're going to melt the polymers. We are going to measure the temperature with a thermocouple. And you see we're going to find essentially a heating and cooling rate. And then you'll see a region where there's a change in slope. Now, this thermal arrest is very exaggerated, except for pure materials. So you'll see this kind of change in slope, and then basically this is where we start solidification, and then you can kind of see where it ends as well. So that's kind of the concept that we are working with here. So we are going to analyze these heating and cooling curves to find where does high temperature, we're liquid, after that here, we're solid. So we are going to use this then to create a phase diagram. So we are going to find essentially, and here's another example where you kind of see this change in slope. It's not exactly just a straight on, flat curve. It's here's my heating and cooling rate, and then I see, here's a change in slope. Here's another change in slope here. So I can identify my liquidus and solidus. If I have a pure material, you may see a curve that looks straight, then one change in slope, and then it's kind of just very flat. So you may only see kind of slope and then slope. Also, if you have an invariant point, you may also observe this as well. So that's kind of a hint for what you're going to do moving forward. So, of course, we want to acknowledge essentially where a lot of these ideas came from. Even though we're not using a differential scanning calorimeter, we would like to acknowledge a wonderful person, Dr. Geetha Barrera, who was my lab instructor and who I was very fortunate enough to teach and TA for this particular lab. So she is you have to give credit, she is the designator for this lab. She is also a wonderful person and experimentalist. She's fantastic. So I will see you all in the video about how we're actually going to use a hot plate to measure this, and catch you all next time, and then eventually in the analysis. So see you. Bye.